Okay, let's shift gears a little bit. So we've been looking at this function for a long time, and you can see I've shown you 8 different ways to draw the schematic diagram for it. And can I do it with fewer gates? I ended up with a bunch of 3-input AND gates and 1 4-input OR gate, which maybe I made out of a NAND gate using De Morgan's theorem, or maybe I made it out of a tree of OR gates because I only have 2-input gates. Can I just make something simpler? And so here's a bunch of Boolean algebra identities, okay, that you can use to try to simplify a logic equation. Now, by simplification, what are we after? We're after fewer terms, OR terms, fewer product terms, and then we want each product term to involve fewer of the inputs. And if we do so, we're reducing the number of inputs in our gates by somehow shrinking the size of the logic equation. The key Boolean identity we're going to use is what's called reduction. And you can see that in a particular case, if I have a logic equation that's A and B and, just to make sure I'm not A and B, and we think about when is this equation true, the answer is, well, it sort of looks like when B is true, it doesn't matter what A is. So if B is true, B could be a complicated expression, but if the B part of the equation is true, then if I see this in my logic expression, I can reduce this just saying B, right? Because when B is true, it's true when this expression is true whether A is 0 or 1, so long B was true, right? So this is a way of doing this sort of simplification. And in fact, you can sort of say, well, it's pretty obscure, Chris. I mean, let's see it in action. And the answer is we're going to use this reduction identity where alpha is any expression and A is a particular literal. We're going to take this guy up here, which is our favorite expression that we seem to have been working on for a while. Okay, and here it is. I've just rewritten it here. Well, I can see here that I have CB and not A and CB and A. This little guy in the middle is a chance to use my reduction and replace that with the single term CB. So you can see I've gone from 4 product terms, each of which involves 3 inputs, to something now which is only 3 product terms, one of which only involves 2 inputs. My schematic will use simpler gates. And in fact, I can now apply this once more. And I can see I can reduce the original expression, the original sum of products, into a different sum of products, which is using, is now a single 2-input OR gate with 2 2-input AND gates. And that's sort of neat. You can sort of say, wow, this is actually a lot smaller. So this is what we would call a minimal sum of products. I can't reduce this any farther. There's no more product terms to get rid of. And in fact, you could write a program to do that, these minimization programs. The trouble with the minimization programs is that their complexity, how long they take to run, okay, grows doubly exponential in terms of the number of inputs. And you can sort of say, wow, how bad could that be, Chris? Suppose I have a 100-input equation, right? To exhaustively enumerate all the possible combinations of reductions I could do, to write a program to look for that, I would have to explore a vast number of possibilities, far too many to explore in the lifetime of the universe. So these logic minimization programs are really heuristics.